Hey, where's everybody? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21. Hey, how's it going, Daniel? We're, I don't know, 9 short of where we're usually at in class? I know I shouldn't be asking you. You're here. It's the people who aren't here who aren't here. Anyway, for those who are here, I'm just going to write on the board the 4-digit code as soon as it comes up for the attendance. So when you come in, you can take a look at that and don't have to try to read this tiny text in this class attendance thing. I sent you an announcement yesterday. Hopefully you got that. Hopefully you're signed up to receive announcements. That's how I'm going to be sending the bulk messages in this class usually, both so that they don't get lost in your inbox, the same reason, and so that they show up at the top of the modules and the home screen on our page, in our class every time, so you don't have to go looking for that information. Help with the homework this week is due, obviously, Thursday evening, as usual. And help with the last 3 of them that we hadn't really gotten to in class. What we're going to talk about today. Questions about anything? Physics, life, Geneseo. Yeah.
I actually want to make a quick announcement.
Sure.
Hey everyone, my name is Daniel. I will be in the Physics Learning Center today from 3 to 5 p.m. If you guys need any help, so follow on in. It's on Discord. If you need the link, it's on the Geneseo PLC website.
When you say in the Physics Learning Center, you do not mean ISC 232, whatever it is. You mean you will be available on Discord as a tutor in the Physics Learning Center to answer questions about this class, which you're taking right now.
Or any other physics.
Or any other physics class. That's cool.
And then there's another person coming in class.
Okay. And you're good with this week's homework set. Awesome. So I have office hours. I assumed that everybody in this class knew that, but maybe you don't. There is a Physics Learning Center. It's not just for first-year students. Feel free to hop on there. Are there any other people in this class who are tutors? I think the rest of them are taking junior and senior level classes at this point. Everybody else, I mean, Daniel, you're certainly welcome to ask him. I'm sure he knows what's going on in this class. But everybody else has taken this class already and has already done all these problem sets. And we'll at least be able to remember, hopefully, what was going on. So you can utilize that as a resource as well. Thanks. Anything else? Okay. Let us then yay, it just works. Move on to our next topic, which is waves changing media. And I'm going to close out this attendance thing because I think we've got everybody. This thing can go away. So, as you probably have learned at some point along the way, when light passes into a medium that is not vacuum, things about that light path and progression and propagation change. I've got a quick demo here. If you're zooming, hopefully you can see this. I've got a paperweight. This is actually the paperweight for the dedication of the Omega EP laser at the University of Rochester Lab for Laser Energetics in 2008. Been sitting on my desk ever since, but it's kind of a cool, if you can even see this, because it's glass, it's kind of hard to see what the shape is. It's got a flat bottom, but a rounded surface. It's not spherical, but it's definitely a rounded surface. So what I can do, I've got a laser pointer here, I can point it at the wall. You can see the progression of the laser pointer. I'm not going to change the direction I'm pointing the laser. I'm just going to move this in front of the laser. And you're going to see how the location of the spot and the size of the spot changes as I move the lens, basically a giant lens, across the board. Again, I'm not really changing the location of the spot. You can see the spot does get really big. It becomes out of focus. And I can move the location of the spot simply by moving the location of this lens back and forth in front of the laser. And that's because the laser, as it enters the light, as it enters this glass, will change direction as it enters the glass, and then it will actually change direction again when it leaves the glass. And both of those correspond to where the spot actually ends up at, which is a function of what the angle that it enters the glass in and the angle that it leaves the glass in. So that's what we're going to be discussing now. Light waves are bent as they change media. How are they bent? Direction of propagation changes. There we go. That says changes. How does it change? This is Snell's law. So, Snell's law, you've got is this. N1 times sine theta 1 is equal to N2 times sine theta 2. What does this mean? So this is telling us, oops, go away, how the angle of the wave changes. But which angle is this? It's important to define what your angles are. If you have some surface like this, and you have some incident ray like this, theta, there are two logical ways to measure theta, with respect to the surface and with respect to the normal. This theta is with respect to the normal. So there's your theta 1. In some medium, you go to a different medium that has a different n value. We'll talk about what n is in a second. And theta 2 might be different. That angle will change relative to the normal as it enters the medium. What is this n thing? What do we call it? It's called an index of refraction. Let's do some greatest hits. Index of refraction's greatest hits. What is the index of refraction of so this is medium and n. What is the index of refraction of a vacuum? It is defined to be 1. What is the index of refraction of air? Pretty darn close to 1, but not exactly 1. You're actually going to measure it in lab this semester to very high accuracy. You're going to use interferometer. You're going to pass laser. It doesn't matter how you do it. Anyway, it's about 1.3 zeros and a 3. It's almost exactly 1, but it's a little bit bigger than 1. In fact, in any medium, the index of refraction can only be bigger than 1. You will never have an index of refraction less than 1. Water. They know what water is? 1.33. Glass. It depends on what kind of glass. If there's stuff in the water, it can change things slightly. These are all approximate values. 1.52 or so. They know what I shouldn't say this. The largest natural index of refraction occurring, it might not be, but it's very large. I'll just write it down. Diamond has a very large index of refraction. 2.42. So that's pretty big. So what are these measuring? Index of refraction. This process of light entering a changing media and changing direction is called refraction. So the index of refraction is how strongly that substance influences the direction of light power. The bigger the number, the greater the difference and the greater the change as that light wave changes medium. So that's fun. It's not that hard to calculate these things. You can plug in some numbers. You can make it kind of complicated and do some interesting geometries, but Snell's law is pretty simple. It's not that complicated. And it turns out, is also related to some physical properties of the material itself. And that's more interesting. What's actually going on inside the property? It's related to how slow light moves in the medium. For instance, n is also equal to c over v, where c is the speed of light and v is the speed of propagation of light in that medium. So c, light in vacuum, speed of light in vacuum, v is in medium. And since light can never travel faster than the speed of light in any medium, c over v is always greater than 1 and n is always greater than 1. So how is it that light can slow down in a medium? This is an interesting question. It was a rhetorical one, unless somebody wants to try it. Go ahead.
It's going into where does it matter? It's still going the speed of light on the side, but it's getting bounced around a lot. So it's
Yeah.
not in a straight line.
So the answer was it's still going the speed of light, but it's kind of bouncing around in there. There's more atoms and bounce off of it. There's two ways to think about what's actually going on. One is the quantum way, and that's the way that you're talking about now, where individual photons are probably bouncing and being scattered by individual atoms within the matrix of whatever substance you've got there. That's certainly one way to think about it. Yeah.
The other way, think of it that it's like a wave, it would be like a physical, like sound wave moving through the medium. So basically, charge a particle, bump into another particle, take more energy, go into the vacuum. So it has to take time to jump between each basically particle through the medium before it exits it, or not.
Probably you could break down what I'm going to say into explaining it in that way. I'm going to use a much simpler analogy, a much simpler explanation. We've already seen that Maxwell's equations define what the speed of light is. Right? C is 1 over the square root of what? Mu naught times epsilon naught. What are those mu and epsilon naughts? And what is the naught specified? That is the permeability of free space and the permittivity of free space. Of free space, the permittivity and permeability of free space, of a vacuum. When you are talking about a different substance like water or glass, there are mu values that are different than mu naught. There are epsilon values that are different than epsilon naught. How easily, what is mu naught and epsilon? Basically, how easily electric fields can propagate in these media. And the harder it is for these, so V is still 1 over the square root of mu epsilon. It's that mu and epsilon are changing inside that medium due probably to processes that you're talking about. So why is V smaller? And the answer really is that mu and epsilon are larger. It is harder for those fields to exist in those places. And so V is still 1 over the square root of mu and epsilon, or mu times epsilon. But mu and epsilon are not mu naught and epsilon naught. They change depending on what the medium is that you're talking about. So, in terms of the classical way we've been thinking about how light works, it's simply that it's harder for these waves, these electromagnetic waves to propagate, and therefore they do it a little bit slower. The physical properties of the substance matter in determining how fast that wave propagates. It's just mu times epsilon. I'm not sure why I put a little dot there. Yeah, okay, I've explained all that. So, let me bring up a quick animation. There it is. Right, and I need to do some cleverness. Whoops. There we go. Okay, so this is a FET animation. FET is a bunch of animations that were developed in the University of Colorado. That did not work, did it? I should have tried this before I came to class. Open this web, you need to download the Java runtime environment. Oh, crap. See, I got a new laptop over the summer, and I haven't even installed Java. We'll play with this next time. You can look this up, though. This is the bending light animation, FET animation. You can download it. The PHET is the name of the site. You can download this animation and play with it. It's kind of cool. You can play with different angles. Maybe I'll actually start this download, because it is kind of fun to see. Could do it till next time, but Java website, you will need to download the Java runtime environment. Fine. Yeah, I just sort of have to describe this and how it works. Well, okay, allow, sure. Why not? All right, let's see if this works now. Open this. I just did that. Oh, that's sad. Oh well, it's not going to let me do it. I'll figure this out and we'll play with it next time. There is a, I'll just describe what's going to happen. It's interesting. Again, the example that I just did above, and let me just draw this, right? If you have an incoming ray, and you have an N1 and an N2, the way it's typically drawn is this, right? Here's your normal angle, here's your incoming and outgoing angle, and it's almost always drawn such that theta 1 is bigger than theta 2. That only happens if N2 is bigger than N1. This is usually what you're talking about. You're talking about light and air hitting some lens or some water or something like that. If it goes the other way, if you're talking about light that is inside a piece of glass or a piece of plastic or a piece of body water, and it's going from higher index of refraction to lower index of refraction, it goes in a different way. So this is N1 less than N2. If you have N2 less than N1 in the other direction, you can get a different scenario happen, right? So if I have some incoming ray at some theta 1, the outgoing theta 2 is going to be bigger. this is N1 greater than N2, right? And this sets up an interesting case. Interestingly, so let's think about the first one first. There's going to come a point at which as this gets smaller and smaller, well, let's do the bottom one, because this is one is more simple to understand. As I make theta 1 bigger and bigger, theta 2 also gets bigger and bigger and bigger. There's going to come a point where theta 2 becomes greater than 90 degrees. Right? That has to happen. A theta 1, if you make it any bigger, theta 2 is going to get bigger than 90 degrees. What happens then?
Is that the critical point?
The wave is going to be completely reflected. I heard you on Zoom, and you said something about a critical point, and that is, in fact, we're going to call that a critical angle. But if theta 2 becomes greater than 90 degrees, then you have total reflection. None of that wave can physically even get out of that medium that you are in N1. So you get a situation where if theta is a little bit bigger, then none of it gets propagated through to that material, and all of it will get reflected back. There's no physical way for it to escape the medium that it's in through that barrier. You can, all light is reflected. What incoming angle does this happen at? We can actually calculate it pretty easily from Snell's law. We have Snell's law up here, N1 sine theta 1 equals N2 sine theta 2. All you have to do is set sine theta 2 to be 90 degrees and solve for theta 1. So let's do it. So N1 times sine theta 1 equals N2 times sine theta 2. As theta 2 goes to 90, sine theta 2 goes to 1. And this becomes sine N1 times sine theta 1 is equal to N2. Or, if you like, sine theta 1 is equal to N2 over N1. Or, if you like me to do my inverse trig for you, theta 1 is equal to the inverse sine of N2 over N1. And let's call that the critical angle, theta c. If the incoming angle, and this is a minimum, right? It has to be your theta, your angle of normal has to be greater than the critical angle for you to get total reflection. So let's do an example. Glass to air. So N1 is about, let's just make some round numbers, 1.5, and N2 is about 1. What is the critical angle of glass to air? Theta c is inverse sine of 1 over 1.5, which is the inverse sine of 2/3, which is about 42 degrees. So you've got some situation where this is glass and this is air. And if you get an angle of 42 degrees, if this is theta C, then your projected output would be right along the glass, and that doesn't even work. Any less than that, any angle that's smaller than that, and you'll have some angle into the air that works. Any bigger than that, and there's no angle that can possibly work to get that light out of the glass and into the air. And all of it will be reflected back into the glass itself. An inverse mirror, if you like. Instead of the mirrors that we think about being air to glass, this is a glass to air mirror that doesn't require any silver. Doesn't require you to paint anything. It just requires that change of medium. Is enough to keep it totally eternal reflection. Okay, a couple of notes on this. This only works in going from high end to low end. For N1 greater than N2. If you've got a situation the other direction, you can make mirrors, but it isn't based on this property. It's based on other properties of the material themselves. And the second, the angle, again, these are all with respect to the normal, must be higher than the critical angle for total internal reflection to happen. So this is a minimum angle for total internal reflection. Okay, there's a cool application for this, which is fiber optic cables. So how do fiber optic cables work? Well, you've got some very long wire of some clear material. Plastic, glass, water, it doesn't matter what it is, as long as you can keep it confined to a tube and make it surrounded by material whose optical properties are a smaller index of refraction. This can work. If you can get that light in to the surface, in the end, then what's going to happen? Well, as long as this angle is greater than the critical angle, it's going to have a total internal reflection. And as long as this angle is greater than the critical angle, it's going to have a total internal reflection. As long as this wire and this cable is fairly straight, this light path should progress indefinitely down this path. There should be nothing that prevents all of that light. You'll have total internal reflection down the whole thing. This thing can even make small turns and bend around corners, and that light will stay inside of the fiber optic cable. Usually the way this is done in practice is you've got some plastic material that is the fiber itself, and you've got some cladding around it, because you can't just sheathe this in plastic, right? It's got to have some material that it could go into if it had the right angle for this to work at all. So usually it's encased in some other called cladding that just is a material that has a lower index of refraction. And as long as that difference in index of refraction is big enough and the incident angles are large enough relative to the normal, then this will work. Then you can enclose that in whatever you want to and roll this thing out for hundreds of miles if you want to. And your only really losses are going to be absorptions by impurities in the glass or the plastic itself. Very good at transmitting large amounts of information and light signals very quickly over very large distances, because light moves pretty fast. I've got a quick and cool example of that. Let me stop sharing so that the Zoomers can see what's going on. Here I have an equivalent of a fiber optic cable, right? So you can see this on Zoom. go. You can see. It's got two ends, one here, one here. This does a little curly Q before going out. The cool thing is, I can use my laser and shine it in one end, and you should be able to see this end. If I turn off the light, I don't think you're actually going to be able to see it propagate through the thing itself, but you might be able to. Turn this off so you can see it. Oh, that's darker anyway. Okay, so here is the laser. You can see it on the ceiling. I'm going to point it so it hits this thing, and you should see it not only not hit the ceiling anymore, you should see this end light up because the laser pulse should go all the way around and come out this end. Ready? There we go. Oh, you can't even see it light up. That's pretty cool. Right? It's not coming out the top at all anymore. It is completely internally focused inside the laser. And if you even come up, you can see it bouncing before it gets scattered around there. You can actually see it bouncing a few times as it goes around and comes out the other side. Here for the zoomers. You can see this piece light up as soon as I get that under there. So there you go. Even if my electronic demo is not working. Oh, there you go. Oh, yeah, I got the lights to come back on. That's fine. Okay. One thing I forgot to mention. But I did mention it in my announcement yesterday. Let me share again. Is how this change in how the change in velocity actually works. Because there's two ways you can think about this happening, right? If the velocity is changing, you know that wave speed, wavelength, and frequency. Let's think about this now. We're going to talk about this. There's a cool demo on the FED thing that I'll show you on Friday if I can get it working. We know that wave speed, V, is equal to wavelength times frequency, right? So as that wave speed changes, it could be that your wavelength, one of those, for both of them have to change. Either your wavelength or your frequency have to change. It turns out that frequency is constant, no matter for light, no matter what the medium is. Frequency is a more fundamental property of a wave than wavelength is. You can change the wavelength of a wave just by changing the medium property. The frequency, though, will stay the same. So that's an important part. As V goes down in a medium, wavelength also goes down, and frequency is constant. That's important. We could even, it's going to be important for lab, for the last question on the homework this week, figure out how much that wavelength changes, right? We know that N is C over V, right? So we know that C is the wavelength in vacuum times the frequency in vacuum. V equals vacuum. I'll say M equals medium, or some non-vacuum medium, divided by the wavelength in the medium times the frequency in the medium. We know that those frequencies are exactly the same, though. FV equals FM. Those cancel out. And you've got N equals wavelength in vacuum divided by wavelength in medium. It changes. It will depend on what N is. And that was a 3-hump M. That was way too many humps. Okay? So the problem that you have on the homework this week is this. How many, you've got two media here. You've got a light wave where the waves are in phase as they come to each of these media, but they become out of phase as they travel through these different media of different lengths. Your job is to figure out what the wavelength is in here, figure out what the wavelength is in here, count the actual number of waves. Count the actual number of waves. You're going to have to actually count both of them to this point because you want to know at this point here how out of phase they are. Right? So you're going to have to, for the top one, count it both there and there. And then you're going to get a number. So a total number of waves, n in this region and the total number of waves n in this region. And it's going to be the difference in those total number of waves that's going to give you the phase difference. The caveat being that let's say you get a number and that number is 1.6. 1.6 is not the answer to this question. Why not? It wants the phase difference between these two waves. It wants the smallest number of wavelengths that you can move one of these waves to bring it in line with the other. So you don't care about the full phase difference. You can ignore the one, you can ignore any integer really that's there. You want to know what the fraction is. And the answer is even 0.6. Because if you're 0.6 of a wavelength away from this phase, you're 0.4 of a wavelength away from this phase. The answer to your delta was 1.6 would actually be 0.4. That's how the shortest distance you can move this wave and get it lined up with this. The answer to the last question, I think it's 18 on homework, will always be a number between 0 and a half. It cannot be anything other than that. That's a pretty good hint for that. I'll get this fed animation working and we'll play with some stuff on Friday. For now, we can move on. To a different topic. And that topic is interference. Okay, so first some history. People have debated for centuries before we figured out what it was. We still debate what it is, though. It's a very interesting topic, and we still don't completely understand it. What is light? Actually, if you go back to Newton did all kinds of experiments on all kinds of things, but light was certainly one of the things he was most interested in. He did a lot of experiments. And he, this is the 1600s now, he postulated that light was a particle. And he called those particles corpuscles. If you ask me what experiment he did that made him think that, I won't be able to tell you. There's probably a good Wikipedia article about that. But it's not, so us thinking of light as a particle in the postmodern physics world is a change from the 1800s, but it's not a change from the 1600s. People were thinking about light as particles even before we started thinking about it as waves. And this only really changed to our wave way of thinking about it in the classical pre-quantum mechanics world in the 1800s. And there was a guy named Young who did a famous experiment that involved light and two slugs. And you can really only understand the results of that experiment by the wave theory of light is an actual wave. So let's talk about, so 1600s, let me just quickly get down. Newton, light is a particle. And so far in this class, we've been talking about the post-1800 but pre-1910s world, where Young and his experiments certainly showed that light is a wave. And certainly, Maxwell would agree with that, right? Maxwell, the theoretical side of all of this that we've been developing until now, certainly backs up the idea that this is a wave-like property. So, why did he do this? Basically, he did experiments involving interference. And particles don't really interfere with one another, but waves do. So how does interference work? Here's the basic idea. These were interference experiments. Here's the basic idea. If you have two waves and you line them up together, they can add up in a number of different and interesting ways. They can add constructively. In other words, if you've got one wave that looks like this, and you've got another wave that is in phase, in frequency, and in wavelength, and in wave speed, and in phase, you add those two up, and you get a wave that has the same frequency and double the amplitude. I didn't draw that very well, but it should have the same frequency and wavelength and double the amplitude. They can also add destructively. Again, if you have a wave and a second wave that has the same wavelength, the same frequency, and the same wave speed, but is 180 degrees out of phase, it will look like this. And if you add those two up, you get that. They are completely destructive. Both of the waves are, wherever there's a positive one, there's a negative one on the other side, and adding those two amplitudes up go to zero. If you've ever, you guys are too young to have ever had a telephone or side of this, play with any rope or string that has some mass to it, and just play with vibrating up and down and make waves on it. That wave will propagate backwards. If you do it at the right frequency, you can get nodes to show up in your string, in your wave. There'll be regions where it's bouncing up and down, and there'll be regions where it isn't moving at all. You've got two waves there. One's propagating in that direction, it reflects off of wherever it's being held still and comes back in the other direction. Those two waves, if you have the right frequency, will add up to an infinite number of wavelengths. And some places those waves will always be adding, and in some places those waves will always be interfering in this effect. The amplitude in some of those regions will be really high, higher even than what you're doing here, and in some of those regions it will be zero all the time. That's when the waves are actually destructively interfering, giving you zero. So this can happen with any wave, including a light wave. So, with a wave on a string, this is pretty easy. With sound waves, this isn't even all that hard. Those are simple waves of a simple medium. Ocean waves, similar thing. You can get, if you have two waves coming in different directions, you'll have regions where it's really high and regions where it's really low, where these waves add and constructively and destructively. Light waves are harder to do this for. They're much more complicated things because not only do you have direction of propagation, you've got direction of electric field and direction of magnetic field. And if either of those are tilted by a little bit, you're not going to get any sort of interference at all. Right? You have to have, there has to be some property of the light that is the same for this property to happen. So in other words, if I had two sources of sound in the ceiling here, I could move to certain places where I would be hearing a lot greater than I normally would, and move to certain other places where I would hear almost nothing because those waves were interfering. That doesn't happen with lights in the room. And that's because of something called coherence. So, under what conditions? light from multiple, you've had this. Go in your room, turn on 2 lights and 2 lights only, there won't be regions where you're seeing interference patterns. So, they must have the same polarization. That is the case if you've got an electric field pointing in this direction, an electric field pointing in this direction. Even if they're out of phase, they're not going to interfere with each other because they're pointing in one. So they must be polarized, and they must be the same polarized for 2 waves to interfere with. And the second term is a little bit harder to understand. You need something called coherence. Coherence means the phases of the 2 waves must be in sync and not changing with respect to each other. This may sound like an obvious thing, but if you have a single light source, if you have 2 light sources, even if they're going through the same polarizer, those phases can drift slowly on the light scale, but rather quickly on our ability to sense it scale, and you need those phases to be drifting in the same way. If they're drifting back and forth with respect to one another, you're not going to get the same kinds of properties of the interference. Right. So that's basically what coherence means. They need to be lockstep in with one another. It turns out that these light sources can wander even as they travel through space. That phase can move a little bit for a single source. Interestingly. Even on the order of 10 meters or so, the phase can have wandered a little bit, and you're not going to get the same kind of interference that you got before. So, how did Young solve this problem? He took a single light source, and he split it up into 2, and then he re-merged it back together. You've got a single light source, you don't have to worry about the coherence sort of is built in, because it's the same source, behaving in the same way. Just split up. Okay, so here is the situation. Oh, look at that. I have 1 more minute. I'm going to draw the picture. This is going to be 2 slit interference. Here's the situation. You've got a wall, and you've got 2 holes in that wall. And you've got a plane wave. This is supposed to represent the crests of the plane wave as it's approaching the wall, moving in this direction. What happens when a wave reaches that slit? What happens to the wave on the other side of that slit? It does. Interestingly, this wave that was propagating as a plane, before it hit the slit, on the other side of that slit will actually propagate outward as a sphere. And we'll talk about why that is and what it leads to in terms of interference on Friday. Hey. But this can be above 12.5. But if you come to 497, that should be close enough to that, or almost close enough to that. Maybe not, maybe not. Maybe it's just outside the 1%. Maybe that's just outside the 1%. Yep, give it a go. Okay, Zoomers, good to have you. See you Friday.